I would like today to talk about extended statistics and our new extension, which we designed for free to nudge a discussion of in the community about statistics and how to improve it. Being invented introduced in Postgres 12, it still doesn't work quite rarely in real installations, as I see, because people at first afraid overheads because they don't know how difficult it would be for vacuum, and the second reason is because they don't know on which set of expressions or columns create extended statistics, and our solution tries to resolve both of these problems in some way. Working for Postgres till 2017, a contributor to core, I designed some features which help optimizer to be more smart. It's adaptive query optimizer based on machine learning. It's a plan freezer. It's replenisher. Today it was committed or any transformation, and so on. And most of my features was designed according to query-driven approach based on queries. And I see for some time how it works and see that it have weak points because of architecture of Postgres. And this time we tried to implement our new extension according to data-driven approach, and maybe it makes sense. Just to understand what we are on the same page, I want to tell something about a bit about extended statistics, how it works. You can easily find much more detailed explanation in Thomas Wonder's speech on PGConf Deutschland 2022. You can follow the link in this QR code. But in simple words, create statistics needs to define table and define number of columns on which you create the statistics. And after that, extended statistics will try, this model will try to find dependencies in between columns of the data. Unfortunately, we can create statistics only on one table, and it's the reason why it doesn't help with joins, with more complex structures, just with single scans. Right now, extended statistics contains three types of statistics. At first, it's most common values. It's values which frequently you can find in the database, in the table, and number of distinct values, which calculates around all possible combinations of columns you use in these statistics, and dependencies. It tries to identify functional dependencies between separate columns or combination of columns. If we will try to understand how difficult it is to calculate extended statistics, let me show you. MCV, most column values, it's just the two arrays, values and their frequencies in the table. So increase the number of columns, you just increase the size of value. It's maybe not so difficult. Distinct number, because it's just a one number, it's not so much, but it calculates on each combination, and it's a lot of combinations. For example, for 8 columns, we have about around 250 different combinations. With dependencies statistics, it's also one float value, but we need to calculate for 8 columns already about 1,000 number of different combinations. It's definitely too much. So in my opinion, we should somehow differentiate in a vacuum analyze command, calculating plain statistics on each column, and extended statistics, at least give a database administrator chance to decide what to do, just to don't get a lot of overhead. this extension, how it works. Just to show how it works, you can see on this example. To use this extension, you need to create, as usual in Postgres, this extension, and after that, adding any table and indexes on this table, you immediately will get in this database new extended statistics. These statistics will be defined over definition of indexes. Of course, as you can imagine, people like indexes in the database, and they can create a lot of indexes over one table. So we should think about compactifying, and we are trying to do this approach this problem. Right now, we just remove duplicated statistics, but we have a room for improvement here. Yeah, and we limit number of columns in the definition, because as you can see before, if someone will define 10, 15 columns, index on the 10, 15 columns, we can stuck into the problem of computations, and we limited that and added parameter. Also, to manage the problem of removing unneeded statistics, we added dependency on of each auto-generated statistic on extension and on index. And if you will delete index, you immediately can see that also after that, statistics based on this index will be removed from the table. So if you delete all indexes, you delete all auto-generated statistics. And if you delete whole extension, you immediately delete all auto-generated statistics in this database. Also, we added some comment to auto-generated statistics, and database administrator can make scripts according to this format and this command, just to check how many statistics he has. Oh, sorry. Yeah, and work out some problems maybe. Also, we added a couple of hooks and functions in this extension. For example, mode, how aggressively you will create statistics in the database. Limit on columns. Who knows? Maybe you want 10 columns, and you will work out somehow computational problems. You can generate statistics on specific table. You can generate on whole schema, all tables in the database except system catalog, and you can remove some statistics on some table or some subset of tables. Short stage dive into the implementation. During this implementation, we found out that it's not easy for Postgres, not natural, to create an object during creation of another object. And because of that, we made it in 2 steps. First step, we use object access hook and gather candidate object IDs, which can be used to generate statistics. Because on this stage, we can't differentiate tables, indexes, create views, and so on. And second step, after successful execution of utility hook, we already can differentiate tables, type of tables, indexes, and so on, and we already know their names. And on the second stage, we create these statistics, set dependency on extension and on index, and adding a description for these statistics. And what is the reason why we started this work? This work was started because of a growing flow of queries, complex queries, which contains a lot of clauses, a lot of joins, and so on. And the reason for that is object relation mapping systems and REST APIs. And the number is growing, as I see, according to our experience. And I guess they will manage bigger and bigger databases, and we should understand how to work out this challenge, how to work with queries which can contain quite stupid set of expressions. Remember that Postgres was created in assumption that people manually optimize their queries and contains a minimal number of expressions. Analyzing such complex queries, they divided them into two classes. It's base relations, scans, and another relational operations like joins, groups, sort, and so on. For the top, for complex relational operations, we already have a lot of tools. We have adaptive query optimizer, replanning feature, plan freezing feature, selectivity by index, a lot of stuff to help optimizer to plan query correctly. But for the low level, for simple scan, we can't use these complex extensions, complex helpers, just because it adds a lot of overhead, too much for simple scans. And here we have only statistics, and we should work with that. To show you how problematic it can be, I could show you simple example. Here I get a database accessible freely, global power plant database containing only one table with a lot of columns and contains a lot of information. And here we have just a simple query, just simple selection. And as you can see, if we select by country, short name of country, we get accurate prediction of number of resulting rows from the table. But if we add in this expression just a long name of country, long description of country, we get underestimation, very bad situation, and we can get into the nested loop scan and so on. In the case of join, it's just because plain statistics don't know anything about correlations between columns. Of course, we have strong correlation between name of country, short name of country, and long name of country. Yeah, and we stuck into the problem. And our conjecture was databases has all the data they manage, but also they know all things about incoming queries. And because of that, future generation of databases should somehow predict, should somehow see into the correlations between data and should find some templates of queries. And according to that, we maybe they should invent some new types of statistics, who knows. Why we use indexes as a template to generate extended statistics? Here is a real example of table named parcels and 8 indexes on this table. It's from a real database, from a real user. And as you can see, people create the indexes, keeping in mind that they will get index queries according to these indexes. Yeah, so it's kind of template. And if we will create statistics based on this template, it's quite probable that we will resolve problems of prediction for most queries, at least most crucial queries in this database. And we tried to use it. Using that, we made some experiment. The same database, global power plant database. We compare plain statistics, extended statistics, and actual number of rows. We added to the clause, where clause step by step, different expressions. And you can see how prediction changes, prediction of cardinality for this select. As you can see, plain statistics do some a bit quaint prediction because it didn't know anything about correlations, and sometimes it overestimates real results, sometimes underestimates. But extended statistics makes quite accurate prediction all the time, except the last one, the last expression, because last expression is an equality. Extended statistics made in a way that it can't be used with inequalities, and it's a problem. But with inequality, what can help? Usually, we use histograms. When we need to estimate inequality. In general, in usual histograms can't work properly because we don't know anything about order of clauses. But in our case, we base our solution on indexes. We know which columns will be used in queries we need to estimate, and in which order. It's more important, in which order. So in this case, we can use histograms which already implemented in Postgres core. And we tried to do it with a simple patch. It's already not an extension, but just for experiments. And how we estimate selectivity of see into the clause, into the expression, and trying to find bins in the histogram which can contain this data. So we look for left boundary and for right boundary, and see how much tuples can get into this histogram. Sometimes it overestimates our data, but definitely don't underestimate, and it's already a good result. And we tried to we made experiment after implementing this histogram in this extension, and the same query, same database, and the same number of clauses expression. As you can see, histogram follows the estimation of extended statistics quite properly, and allows us to make a good prediction on the last step, where we use inequality. It works better than extended statistics right now. Of course, such a good result it's because of specific of experiment. In the database, we have a lot of rows, but in each column, we have not so much distinct values. And because of that, histogram covers our data quite precisely. It's non-typical, but it just shows us that we can work with inequalities, and it adds some new case which help extended stat. And maybe here we need to add histograms into the core as a part of extended statistics. And that's it, what I wanted to talk today. So if you have any questions, you can ask them. If not, you can just follow the links. One link is to the extension we invented. It's for free. It's BSD license. Use it on your own. And second one, it's just a company where we work and implemented it. That's it. Thank you.